Welcome back to Numerical Analysis, everyone. Today is Friday, March 27th, and we're going to talk about power series solutions to ordinary differential equations. But before we do that, I wanted to take a look at a little bit of housekeeping we need to do. There's a homework that's due tonight, and that's homework 18. Here it is. And there's a couple of problems on it. The first one gives us an initial value problem and presents the general solution to the ODE and just asks you to verify that, and then asks you to find the constant C that makes the general solution satisfy the initial condition and therefore makes it a solution of the initial value problem. And then in number two, there's an initial value problem with an initial condition at time t equal 2 here. And the problem asks you to put it in standard form, which you may recall from the video lecture before. Standard form means that the initial condition is at time t equals 0. Actually, let's take a minute here and look at the Canvas page and make sure we're all on board with where you can find those videos. If you go to our Canvas homepage, I've organized it so at the very top there's a link, there are a series of links to pages that contain videos on the topics we've been discussing since we've been in the online mode. So the one that's relevant to homework 18 is the page on ordinary differential equations, and if you click on that, you can see the 3 videos already there. And video 1 is the one that is directly tied to homework 18, and so you'll see examples in that video that are directly related to the problems in homework 18. There's another homework due Monday, that's homework 19, and let's pull that up if we can. So homework 19 takes us a little bit further. In the subsequent videos, we talked about the fact that an initial value problem gives you information about really all the derivatives of the function evaluated at the initial time. And so in this homework, I'm asking you to extract that information from 2 different initial value problems. So again, there are videos that address this, and again, they're on that same page in the Canvas. Video 2 is where we introduce the idea, and at the end of video 2, I gave you a practice problem, and actually video 3 just goes through the solution of that practice problem. So videos 2 and 3 are directly tied to homework 19, and I hope they'll be able to help you see your way through that. So today we want to take it one step further and see how we can use that information. Basically, that information we extract from an ODE about the derivatives to form a power series solution for the differential equation. So let's jump right into it. We've seen that an initial value problem gives information about the derivatives of all orders for the solution of an ODE. And the 2 examples that were in videos 2 and 3 were these here. In example 1, we have a simple initial value problem. Dx dt is 2x, x of 0 is 3. And in the second video posted on the page back there, we saw that this implied we were able to determine that the nth derivative at 0 of the solution has to be 2 to the n times 3. And this is true for n, any non-negative integer n. Then in the practice problem that was at the end of video 2, and that was actually solved in video number 3, we looked at this ODE, dx dt equals x plus t squared, x of 0 is 1, and we saw that, again, we could extract all that information. We could extract the derivatives of arbitrary order at time t equals 0 from the initial value problem. In this case, it turned out that the derivatives at 0 were equal to 1 if the derivative, if you're looking at the 0 first or second derivative, and then any higher derivative evaluated at 0 was 3. So we're going to go ahead and use that information now to develop power series solutions to both of these ODEs. So how would we do that? Well, essentially, this goes back to Taylor series and Taylor polynomials. So remember that you can form the Taylor polynomial for a function by simply knowing its derivatives up to a certain order at a given point. So here, since our initial condition is that t equals 0, we're going to form the Taylor series or the Taylor polynomials centered at 0. So this is just the form, the general form for a Taylor polynomial. It may look a little different because usually, I think before our variable was x and our function was f. Now my function is x and my variable is t. But it's the same formula, just using different variables. So the nth Taylor polynomial is the sum of the kth derivative evaluated at 0 divided by k factorial times t to the k, where k runs from 0 to n. So that's a degree n polynomial. And here we're going to also look at the Taylor series. The Taylor series is essentially just an extension of the idea of the Taylor polynomials, where instead of cutting off the series at degree n, we consider the infinite series from k equals 0 to infinity of the same terms. So this was a concept that typically you see in calculus, like in calculus 2 or calculus 3. One way to think about the Taylor series for a function x is it's the infinite degree Taylor polynomial. Of course, it's an infinite series, so there's always questions of convergence and so on for things like that. But for the kinds of functions we're going to be dealing with, those questions are going to be answered in the affirmative. Usually, a Taylor series will converge to the function that you want it to. But just to keep us sort of aware of the fact that sometimes a Taylor series for a function x can actually either fail to converge or it might converge to some function that's different than x. I've written the Taylor series this way, as x hat of t. Now, again, I want to emphasize, in most cases, in fact, I think in all the cases that we'll consider, x hat of t will turn out to be equal to our solution, x of t. But there's always a possibility that that won't happen. And so I'm keeping that alive. I'm keeping that in front of us in the notation by using the little hat. So the Taylor series for a function x, we're going to denote by x hat here. So, just to sort of connect this to the previous work we've done, these derivatives that form part of the Taylor series and the Taylor polynomials, those are exactly the things that we derived in our previous videos. And so those are exactly these numbers here that we were able to pull out of the initial value problem. So since you're able to pull those numbers out of an initial value problem, at least in principle, relatively easily, then it makes Taylor polynomials and Taylor series natural tools to work with when you're trying to solve an initial value problem. So let's see how this process would work for the two examples that we've been discussing up to now. So remember our first example, it was the initial value problem, dx dt is 2x and x of 0 is 3. And we saw in our video number 2 that this implied that the nth derivative of the solution at t equals 0 has to be 2 to the n times 3. for n equals 0, 1, 2, 3, and any non-negative integer. So we can just plug those values into the formula for the Taylor polynomial, and we'll get the Taylor polynomial for the solution. So here again is just the general formula for a degree n Taylor polynomial. Now we're going to plug what we know about the derivatives evaluated at 0, namely this, into that formula. And so we get that. So x super k evaluated at 0 would be, from our formula up here, 2 to the k times 3 over k factorial. And that is then the degree n Taylor polynomial. I've just written it out explicitly here. I've gone ahead. The 3 doesn't depend on the summation index k, so I can pull it outside the sum. So I've just factored the 3 all the way outside the sum. And then the 2 to the k times t to the k, you can just write as 2 times t raised to the k. And so this is the Taylor polynomial for our solution. So that's progress right there, because we know that Taylor polynomials are good approximations to a function near the center of the polynomial. But we can do even better than that looking at the Taylor series. So again, we're still talking about the same problem. The Taylor series for the solution, that would be our x hat, is just sort of the infinite degree Taylor polynomial. So we're just going to do the same basic idea, except we're not going to cut off our sum at k equals n. We're going to let k run from 0 to infinity. So again, the xk's come from our previous work, and that gives us this expression. And now we can manipulate that series and actually recognize it, right? So again, I'm pulling the 3 out of the series since it doesn't depend on k, and writing 2 to the k times t to the k is just 2t to the k. And then, so we have this series here, 2t to the k over k factorial. And so we recognize this as the Taylor series for e to the x. So that may be something you'll need to review from calculus. And so let me just kind of remind you of that real quickly. There are some basic Taylor series that are very well known and very useful to just have at your fingertips in problems like this. And one of them is for e to the x. And so the Taylor series for e to the x is this summation k equals 0 to infinity of x to the k over k factorial. And so that would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... That pattern continues. And so what we've done in that last step in that previous slide is simply recognize that this series is the same as this one, with my x replaced by 2 times t. So the series here is just this series, except x is replaced by 2 times t, so it's e to the 2t. And of course the 3 is still there. So that's a very handy series to have at your disposal when you're trying to recognize a power series as some known function. And I'll make sure to post a list of sort of the common, the power series that come up a lot for you to have at your reference as we go through more of these types of problems. So yeah, based on our work in finding out what the nth derivative at 0 was for the solution, we then use that information to create a Taylor series. And we're able to find that the Taylor series for the solution is 3 times e to the 2t. Now, again, because the Taylor series sometimes fails to converge to the function you want it to, it's always a good idea to check these solutions and make sure they actually satisfy the initial value problem. So we can do that real quick. Let's just check it. The way you do that is you just compute both sides of the ODE, make sure they're equal, and then also make sure your function satisfies the initial condition. So if this is our solution, x hat, let's check and see that x hat is actually our solution. So the derivative of x hat with respect to t would just be 3 times 2 times e to the 2t, and 2 times x hat, so now I'm just looking at the right hand side of the ODE, would be 2 times 3 times e to the 2t. So those two things indeed are equal, and so at least we know that solution satisfies the ODE part of the initial value problem, and then just make sure it satisfies the initial condition by plugging in t equals 0 to x hat, so you get 3e to the 2 times 0, and that's just 3 times 1, which is 3, and that's what we had as our initial condition up there. And so we've verified now that we have the correct solution, and we got it through Taylor series. So let's take a look at a second example of this sort, and let me get my papers together here. Here we go. Our second example was dx dt is x plus t squared. Let me get this where everybody can see it. And the initial condition is that x sub 0 equals 1. And so we found, and again this was actually in video number 3, the solution to the practice problem. We found that the derivatives at 0 were given by this expression, so the nth derivative at 0 is 1 if n is 0, 1, or 2, and it's 3 if n is greater than or equal to 3. So a little bit different situation here. But we can still use this information to form the Taylor polynomials. Here I'm being a little bit more careful because of this sort of conditional nature of the derivatives at 0. P0 of t would just be x sub 0 of 0, which is 1. P1 of t, remember P1 in general, would be x of 0 plus x prime of 0 times t. And we know that both x of 0 and x prime of 0 are 1 from our previous work, and so we just get 1 plus t. P2, remember in general, P2 of t is x of 0 plus x prime of 0 times t plus 1/2 x double prime of 0 times t squared. And so again, all those derivatives at 0 are 1 according to our previous work, and so we're getting 1 plus t plus 1/2 t squared. P3 of t, the way Taylor polynomials work, P3 of t is going to be the same as P2 of t plus that next term, which would be 1 over 3 factorial times the third derivative at 0, and then times t cubed. And so P3 of t, there's our P2, and then that's x3 of 0 we now know is 3, and then over 3 factorial, and then times t cubed. And so continuing in that way, you find the nth derivative at, the nth Taylor polynomial. For any n bigger than 3, it's, here I'm picking off those first two terms because the derivatives at 0 were just 1 there. Then the derivatives for k equal 3 on are all 3, so you just get 3 over k factorial times t to the k. And so I'm factoring out that 3 here, and we get that expression for the general nth Taylor polynomial for our solution. The Taylor series would just take that in and replace it by infinity, because you can think of it as the infinite degree Taylor polynomial. And so we get this expression for the Taylor series for our solution. Actually, we can work with this guy and get a closed form of the solution kind of in the same way as we did before. It's a little bit more, well, a little bit different in the way that it works out, but not too much more difficult at all. So let's work with that series. So I'm just actually here, I just want to look at this part of the solution, the series here, and then we'll come back and put it all together at the very end. So that series from k equal 3 to infinity of t to the k over k factorial. Well, what I recognize is that looks a lot like the series we had before for e to the x, except the series for e to the x starts at k equals 0. Here we're starting at k equal 3. So the way that I'm going to bring sort of what I know into the picture is I'm going to write the series from k equal 3 as the series from k equals 0 minus the series from k equals 0 to 2, right? Because this would be the series from k equals 0 to infinity, and then you're subtracting off the k equals 0, 1, and 2 terms right here. So what you're left with is just the series from k equal 3 to infinity. So those things are going to be equal. But then we know that this series is just e to the t. And then this guy right here is a finite series. We can just write it out. When k equals 0, you get 1. When k equal 1, you get t over 1 factorial, or just t. When k equal 2, you get 1, you get t squared over 2 factorial, or 1/2 t squared. So that part of the solution, just that series from k equal 3 to infinity, is e to the t minus that quadratic. And so the solution itself, x hat, remember, was this other quadratic plus 3 times our series. So I have that here. That's the 1 plus t plus 1/2 t squared, and then plus 3 times our series, which we now know is e to the t minus 1 minus t minus 1/2 t squared. And so that is 3 e to the t and then minus t squared plus 2t plus 2, the quantity. So again, using Taylor series, we're able to find a closed form of the solution of that differential equation. Well, at least we think we have. It's again always a good idea to go and check your x hat, your Taylor series, and make sure that it actually solves the solution, solves the initial value problem. So here I'm just doing that. Remember our x hat here is this guy. So here I'm computing the derivative of that. So it would be 3e to the t minus 2t plus 2, right? And that's it. And then here, so that's the left-hand side of the IVP. The right-hand side is x hat plus t squared. So let's see if we satisfy that. So here's x hat, this piece right here, and if I add t squared to it, you see that those two t squareds are just going to cancel. And you get 3e to the t minus 2t plus 2. So since dx hat dt equals x hat plus t squared, right, these two guys are equal, then we see that we satisfy the ODE part of the equation, of the initial value problem. And then let's check the initial condition too. Let's make sure that when t equals 0, x hat is 1. And when you find that, when you do that, you see that definitely works out. And so the solution we arrived at through the Taylor series is the solution of our initial value problem. So it's a powerful method for finding solutions of initial value problems using this idea of first extracting the derivatives at time t equals 0 and then plugging them into a Taylor series to form a candidate solution, and then checking that solution by making sure it satisfies the original initial value problem. So we have, in our case, we can now write our solution is the function we found through those previous manipulations. And notice now I've removed the hat because I've verified that this guy actually is our solution. So we know now that the Taylor series actually converges to a solution of the initial value problem. And so I can remove that hat from the notation. So yeah, that's the basic procedure. I do have another practice problem for you, and let me show you what that is. So this is going to ask you to go through sort of the same steps and find a solution for this initial value problem using these methods. So what are we going to do? Well, we're basically going to retrace the steps we've been doing up to now. The first step is to use the initial value problem to find an expression for the nth derivative of x at 0 for values of n from 0, 1, 2, 3, and on. So you want to find the nth derivative at 0 for any non-negative integer n. That's basically going to be a pattern recognition thing, right? You're going to probably have to compute 3 or 4 derivatives and see the pattern, and then write that pattern down, and that'll get you your nth derivative at 0. And then use those to form the Taylor polynomials for the solution, and then take that to the limit by forming the Taylor series for the solution, and then use that Taylor series to manipulate those series to work out a closed form of the solution for that initial value problem. So give that a try, and I will be posting a video a little bit later where we actually go ahead and work through the practice problem. And your next homework, which is homework 20, will ask you to do this for another initial value problem. So hope this helps. If you're like me, you find this kind of interesting. I think it's fascinating how all these ideas kind of come together, the idea of a Taylor series, and how nicely that fits in with the information you can extract from an initial value problem. So I hope you're having some fun with it, and if you have questions, let me know. As always, stay healthy, stay safe, and I will be back in touch soon. Y'all have a good one.